introducing the talk, Roxanne. And thank you also for having me. It's an honor to be here and talk about our project and what we can do for the environment. So if I share my screen. Yes. That's nice. Okay, I'm going to talk about decentralized sustainable water solutions. My name is Gholamabbas Sadeghi, and I'm from Iran. I came to the Netherlands in 2020, and since then I've been working on solar energy, specifically regarding the water technology. Okay. To first start the session or the webinar, it would be nice to first have a look at the amount of fresh water available in the world. You can see that only below 3% or 2.5% of the total water in the world is freshwater, and below 0.5% is available in lakes and river storage. So basically, we are suffering from the freshwater scarcity, not from the availability, also, I mean, not from the amount side, also from the availability side. So it's really important to think of how we can make freshwater. And normally it is used membrane technology as a most famous one, reverse osmosis membrane technology. But it works with high pressure pumps, and in total, on average, basically, it consumes around 3 kilowatt hour of electricity to produce a cubic meter of fresh water. However, if we use solar energy that we produce fresh water, normally, on average, it uses 200 times more energy to produce cubic meters of fresh water. But now the point is that we can say, okay, RO is much more efficient than solar energy. But the point is that solar is free. So it doesn't matter how much energy it is needed, because it is actually dealing with latent heat. The solar energy is used for latent heat. So that's why the energy is high. But just because it is free source of energy, especially available, abundantly available during the day. So we're not concerned about that. We're just concerned about the technology itself, how we can develop new technologies. So it is definitely much better for the environment than reverse osmosis, if there is a possibility to do that. And normally solar desalination, to turn seawater into freshwater, basically, it works based on the main scheme is evaporation. So the main part is evaporating water, then the salt will be separated from the fresh water, and then we can extract this fresh water with condensation on a cold surface, let's say glass or cover. And this fresh water or distilled water that we produce can be used for different applications, including drinking water and irrigation also. So it can help the society, especially in regions suffering a lot from water scarcity in Africa, India, some parts of India that we know about. And the point is that if you want to use it for drinking water, we do need more post-processing after having distilled water to monitorize and check the minerals to make sure that it is suitable for drinking. But for irrigation, we need less post-processing or post-filtering. And the other application that we at Vetsus are looking into is the natural water cycle, basically. That normally when the sun is shining, the water evaporates from the surface of the sea, and the clouds are formed, and then we have precipitation, and then it will be collected into the sea again in the end. So But the point is that in desert areas, the sun is shining. However, it is just consumed on sensible heat production, or just, I would say, increasing the temperature of the environment compared to the latent heat or evaporation part. So that's why we have less possibility for forming clouds and less possibility for rain, and then we have desert. So what we want to do, actually, we aim to regreen the desert areas, basically. And how do we do that? With basically expanding the solar energy. Instead of heating up the atmosphere, we use it for evaporation, and then we have clouds formed at a lower altitude and more possibility for rain, and hopefully regreen our desert and make more life. However, the question is where, which location fits this technology, because you cannot just have a kind of costly technology somewhere and you don't know if it will work somewhere or not. So one of my colleagues, Sarah Werner, she works also at Vetsus. She has worked on the basically some case studies, and also she has done a lot of modeling, and she came up with the idea that in the regions that are surrounded between the sea and the mountains, the water vapor produced has the opportunity to go up the mountain, and then over there will be lifting condensation level, and then there will be clouds, basically, in a simple term, and then there will be possibility for rain, more than the regions without mountains. And her work was recently published in Environmental Science and Technology, kind of perspective work. And now let's go back to the evaporation part. So our aim is to improve the evaporation, because if you want to improve your solar desalination performance, first you need to improve the evaporation section. Normally, if you heat the bulk of water, that is, let's say, on the seawater, sun is shining on the seawater, the evaporation rate is around 0.5 kilogram per square meter in 1 hour. But that is not enough, apparently, to have precipitation and rain. So in order, as a technology, new invented technology to increase basically the heat localization on the surface, we use a carbon material, black material on the surface to heat up the surface water. On the other hand, we use an insulation foam underneath. Why do we use that? Because we want to keep the heat as much as possible on the surface. We don't want to lose the heat to the bulk, because the evaporation is happening on the surface. And we know that evaporation is interfacial, so we just need to keep the interface hot. In this way, we can produce more than 1 kilogram of water per square meter in 1 hour, because we are basically reducing the heat losses and curbing localizing the heat on the surface only. But there is some challenges in this technology. The maximum you can produce under 1 kilowatt per square meter of light intensity is 1.5 kilogram per square meter in 1 hour. But there are many studies that report higher this value. So we assume the efficiency will be above 100%, that for a single stage evaporation, solar evaporator, it is not possible to have above 100% efficiency. Basically, it's violation of thermodynamics. So we did research on that, and we came across with this fact that in addition to the solar radiation, we have a substantial amount of long-wave radiation in the atmosphere. That basically the atmosphere itself gets the sunlight, it hits up, let's say the water vapor in the atmosphere, the clouds, everything, and then it emits the heat back to the ground, some part of that, and some part of that to the space. So that amount of heat or long-wave radiation, we got the data, the long-wave radiation data from this website, and it's almost half of the short-wave radiation or the solar radiation. So it is definitely considerable to account for the efficiency calculation. And by the way, we also published this work, and you can have a look at it. It's quite more technical than this. And now we know that we have a kind of system. We can evaporate water. We can separate salt from water. But the point is that because we are doing evaporation from seawater, we have the problem with salt accumulation. So with the passage of time, as you evaporate day by day, your evaporator surface, as you see here, day 1, day 2, day 3, it will be accumulated with salt. So then what happens is that the surface will be white. Then it will be, instead of absorbing heat, it will be reflecting the light. So you don't absorb that much of heat. And also, there will be less water available on the surface to evaporate. So you're just deteriorating the system's performance, basically. You're evaporating less, producing less water, fresh water, and then you also need more maintenance. Kind of every day or every week, you need to clean the surfaces, which is also a challenge. As a solution provided by MIT University, they mentioned if we keep a confined water layer at top of the black material, the black surface, then we won't allow the salt accumulation to happen. So always the surface water is getting renewed with the new water underneath. So always the salt is moving. It doesn't have the time to precipitate on the surface. So and they did it for several days, and after several days, they didn't see a lot of reduction in the performance, in the evaporation rate. Basically, is around 1.1 to 1 kilogram per square meter, basically. And also the other point is that about the salinity, because if you don't have a confined water layer on top, the thing happens is that with the passage of time, you're just increasing the salinity of the surface water because the water is evaporating and salt will remain. But in this way, because the water is getting replaced, then also the salinity of the surface will not change. So you will absolutely, it is not that a strong heat localization on the surface because you have a certain amount of bulk water on the surface. So you don't have that much of evaporation rate that you experience without this confined layer. But the point is that then you get rid of maintenance and salt accumulation problem. But you sacrifice a little bit of productivity. That's how it works. And we also had an interview with the Fox Grant about our technology. And we hope that this technology can be promoted and more people do research and work on it, because it's a quite new application of solar desalination, basically. And if it works, it changes a lot. It makes a lot of life. I know that it has a lot to do. It's quite at its earliest stage. We just started that out in just 3 years ago, 4 years ago. And but we hope that we can get something positive out of it. And in the end, thank you very much for listening. I just want to thank FieldFactors for providing us enough facilities to do research, and also the natural water production team, that we do really interdisciplinary and multidisciplinary work. I mean, if I start from the left side, Professor Bert Hamelers, he used to be a full professor at Wageningen University. Now he is the science project manager at FieldFactors, and he's my main promoter, basically. And then we have Henk Miedema, that he is my daily supervisor. He is a chemical engineer. And we also work, this work is also a collaboration with Polish University, Wrocław University of Science and Technology, with Dr. Sławomir Porado, that he works on chemicals and chemical engineering and membrane science. And then we have Franche, the coordinator of our team. She has a PhD in hydrology. And then Mohammad Zakaria from Egypt. He does work on artificial intelligence and modeling, and also vegetation, that because it is also important for us to know that which kind of vegetation can grow in different situations in desert. And we have meteorologist Sarah Barno, that she does modeling in climate, basically. And we also have an agriculture engineer, Jesus, has recently joined our team. And he's a PhD researcher working on using sensors to measure the evaporation in the atmosphere. Thank you very much. If you have any question, you can ask.
Yeah, thank you. Thank you for the presentation. Yeah, if anybody has any questions, please feel free to unmute yourself and ask. From the speakers as well, you're also welcome to ask any questions if you would like.
If no one else has questions, I can ask some questions.
Yeah, go ahead, please.
I'm wondering if you can give some examples of places in the world where this would effectively help, right? I mean, in general, my